Welcome to a gentle journey through the stars, most distant points of light that have guided travelers, inspired poets, and sparked wonder in human hearts for thousands of years. Tonight, we're going to explore the peaceful nature of stars, their slow and patient lives, and the quiet beauty of the light they send across the vast darkness of space. Let yourself relax as we drift through the cosmos, discovering how stars are born, how they live, and how they transform the universe around them. When you look up at the night sky, the stars you see aren't really where they appear to be. They're not even shining in the present moment. The light from stars takes time to travel to your eyes, sometimes years, sometimes centuries, sometimes thousands of years. When you look at a star, you're seeing it as it was in the past, looking back through time. The nearest star to Earth, apart from our own sun, is called Proxima Centauri. It's about 4 light-years away, which means the light you see from it left that star 4 years ago. You're seeing Proxima Centauri as it was for years in the past. Some stars you can see with your naked eye are hundreds of light-years away. The light reaching your eyes tonight left those stars before your great-great-great-grandparents were born. If one of those distant stars exploded today, you wouldn't know for hundreds of years. The light from the explosion would still be traveling through space, making its way toward Earth. There's something peaceful about this delay. This gentle reminder that the universe doesn't happen all at once. That light needs time to bring us news from the stars. Our own star, the Sun, is about 8 light minutes away from Earth. When you feel sunshine on your face, you're feeling warmth from light that left the sun's surface 8 minutes ago. But the journey of that light actually began much earlier, deep inside the sun's core. The sun creates energy through nuclear fusion, where hydrogen atoms combine to form helium, releasing tremendous energy in the process. This happens in the core, where temperatures reach 15 million degrees Celsius, and the pressure is immense. The energy created in the core starts as gamma rays, the most energetic form of light. But these gamma rays can't travel directly out of the sun. The sun is too dense, too full of atoms that absorb and remit the light. A single photon, a particle of light, bounces around inside the sun for thousands of years before finally reaching the surface. It gets absorbed by an atom, then re-emitted in a random direction, absorbed again, emitted again, billions and billions of times. This random walk through the sun's interior takes somewhere between 10,000 and 100,000 years, depending on which path the photon happens to take. So, when you feel sunlight, you're feeling energy that was created deep inside the sun before human civilization existed. Before we built cities or wrote languages, before we learned to farm. That ancient energy finally escaped the sun's surface, traveled for 8 minutes through space, and arrived at Earth to warm your skin. Every ray of sunlight has this long history, this patient journey from the core to your eyes. The sun has been doing this for about 4.5 billion years, steadily converting hydrogen to helium, releasing light that streams out into the solar system and beyond. The sun is a very ordinary star, medium-sized, middle-aged, unremarkable in almost every way except that it's our star, the one we orbit, the one that makes life on Earth possible. It's classified as a G-type main sequence star, which is just a technical way of saying it's yellowish and burning hydrogen in its core. Most stars are smaller than the sun. The most common type of star is called a red dwarf, cooler and dimmer than our sun, barely massive enough to sustain fusion in their cores. Red dwarfs can burn for trillions of years, far longer than the current age of the universe, because they use their fuel so slowly and efficiently. There are stars much larger than the sun, too. Massive blue stars that burn hot and bright. These stars use their fuel quickly, living fast and dying young. A star 10 times more massive than the sun might only live for 10 million years, a brief moment in cosmic time. The most massive stars live for just a few million years before exhausting their fuel and ending in spectacular supernova explosions. But most stars aren't massive. Most are small, dim, slow-burning red dwarfs that will outlive everything, steadily glowing in the darkness for trillions of years. Stars are born in clouds of gas and dust called nebulae. These clouds are vast, stretching for light years, containing enough material to make thousands or millions of stars. The clouds are cold, just a few degrees above absolute zero, and they're thin, far less dense than the best vacuum we can create on Earth. But they're also enormous, and gravity slowly pulls the gas together. Over millions of years, denser regions in the cloud attract more gas, growing larger and denser. These dense cores contract, and as they contract, they warm up. Eventually, a dense core becomes hot enough in its center to start nuclear fusion. When fusion begins, a star is born. The new star ignites, starting to shine with its own light. This process happens slowly, peacefully, without drama or explosion. One moment, there's a cold, dark clump of gas. Millions of years later, that clump has become a glowing star. The transition is gradual, patient, like watching a sunrise that takes millennia. New stars are being born all the time, throughout the galaxy, throughout the universe. Right now, in some distant nebula, a star is forming, beginning its long life of converting hydrogen to helium and sending light. out into space. Young stars are often surrounded by disks of gas and dust left over from their formation. These disks are where planets form. Dust grains in the disk stick together when they collide, gradually building up larger and larger clumps. Over millions of years, these clumps grow into asteroids, then into planets. Our solar system formed this way. The sun ignited at the center, and in the disk around it, planets gradually coalesced from the remaining material. Jupiter and Saturn, the gas giants, formed farther out where there was more material and where ices could exist. Earth and the other rocky planets formed closer in, where only rock and metal could remain solid in the sun's heat. This process of planet formation seems to be common. We've discovered thousands of planets orbiting other stars, and we find them around many different types of stars. Planets are a natural consequence of star formation. When a star forms, planets often come along with it. This means the galaxy is full of planetary systems, countless worlds orbiting distant suns. Some of these worlds might be like Earth, rocky planets at the right distance from their star for liquid water to exist. Some might harbor life. We don't know yet. But the possibility is beautiful and humbling. Stars spend most of their lives in a stable phase called the main sequence, where they steadily burn hydrogen in their cores. Our sun is in this phase now, and will remain in it for another 5 billion years or so. During the main sequence, a star is in equilibrium. Gravity pulls inward, trying to collapse the star. But the energy from fusion creates pressure pushing outward, resisting the collapse. These two forces balance perfectly, and the star maintains a stable size, burning steadily, releasing a consistent amount of light. It's a peaceful balance, a star in harmony with itself, neither growing nor shrinking, just existing and shining. The light from stars travels through space at the speed of light, about 300,000 kilometers per second. Nothing in the universe can travel faster than light. It's the ultimate speed limit built into the structure of space and time itself. At this speed, light from the sun reaches Earth in 8 minutes. Light from the nearest star takes 4 years. Light from the center of our galaxy takes about 26,000 years. Light from the most distant galaxies we can observe has been traveling for over 13 billion years, nearly the entire age of the universe. This means when we look at distant objects in space, we're looking back in time. The farther away something is, the older the light we see from it. Astronomers use this to study the history of the universe. By looking at very distant galaxies, they can see what the universe was like billions of years ago, when it was younger, when galaxies were just forming. The universe becomes a time machine when you look far enough away. Every photon of light carries information about when and where it was created. And by collecting that light, we can reconstruct the history of the cosmos. But let's return to something more immediate, more relatable. Think about the stars you can see on a clear night, far from city lights. There might be a few thousand stars visible to your naked eye. Each one is a sun, a massive ball of plasma undergoing fusion, releasing light and heat. Each one might have planets. Each one has its own story, its own age and size and temperature and composition. Some are young, just a few million years old. Some are ancient, nearly as old as the universe itself. Some are alone, wandering through space in isolation. Others are part of binary or multiple star systems, orbiting around each other in gravitational dances that have been going on for millions or billions of years. Binary stars are actually quite common. More than half of all stars are part of binary or multiple systems. Two stars orbit their common center of mass, bound together by gravity. Some binaries are very close, orbiting each other in hours or days. Others are widely separated, taking thousands of years to complete one orbit. Some binary systems are so close that material from one star flows onto the other, creating swirls of hot gas and bursts of radiation. But most binaries are more sedate, simply two stars gracefully orbiting each other, a cosmic partnership lasting for eons. There are even systems with 3, 4, or more stars all orbiting together. The dynamics of these systems can be complex, with stars pulling on each other, orbits slowly shifting over time. But somehow they remain stable, bound together by mutual gravity, dancing through space as a group. Planets can even form in some multiple star systems, orbiting one of the stars, or sometimes orbiting the entire group. Imagine living on a planet with 2 or 3 suns in the sky, where sunset involves watching multiple stars dip below the horizon. At different times, where shadows point in multiple directions depending on which sun is overhead. The color of a star tells you about its temperature. Hot stars are blue or white. Cooler stars are yellow, orange, or red. Our sun is yellow, indicating a surface temperature of about 5,500 degrees Celsius. Blue stars can have surface temperatures over 30,000 degrees. Red stars might be as cool as 3,000 degrees, though cool is relative when talking about stars. Even the coolest stars are far hotter than anything we experience on Earth. The color comes from the spectrum of light the star emits, which depends on its temperature. Hot objects emit more blue light. This is why a flame burns blue at its hottest point and red or orange at cooler parts. Dot stars also come in different sizes. The smallest stars, red dwarfs, are about 10% the diameter of our Sun. The largest known stars are called hypergiants, and they're truly enormous. A star like Y Scuti or Stevenson 218 is over 1,000 times larger in diameter than the Sun. If you replaced the Sun with one of these hypergiants, its surface would extend beyond the orbit of Jupiter. The star would swallow Mercury, Venus, Earth, and Mars entirely. These stars are so large that their outer layers are thin and diffuse, barely denser than the vacuum of space. Despite their enormous size, they don't contain proportionally more mass because they're so spread out. Large stars are rare. Most stars are small, but the large ones are spectacular, visible from enormous distances because they're so bright. Many of the stars you can see in the night sky are actually very distant giant stars. They're visible not because they're close, but because they're intrinsically luminous, putting out thousands or even hundreds of thousands of times more light than our Sun. Closer, dimmer stars are more common but harder to see. The stars visible to your naked eye are not a representative sample of the galaxy. They're the brightest, most luminous stars, the ones whose light can reach us from far away. Every star you see at night is part of our Milky Way galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. That's a huge number, difficult to comprehend. If you tried to count them one per second, it would take thousands of years. And that's just our galaxy. There are hundreds of billions of galaxies in the observable universe, each containing billions or hundreds of billions of stars. The total number of stars in the universe is staggeringly large, more stars than grains of sand on all the beaches. On Earth, more stars than seconds in the entire age of the universe. Yet, despite this vast number, stars are separated by enormous distances. Space is mostly empty. The distance between stars is so much larger than the stars themselves. If you shrank the Sun down to the size of a grain of sand, the nearest star would be another grain of sand about 10 kilometers away. That's how empty space is, how separated stars are from each other. They're islands of heat and light in a vast ocean of cold darkness. There's gas and dust, very thin, but spread across the light years. This tenuous material is what forms new stars, completing the cycle. The Milky Way is a spiral galaxy shaped like a disk with spiral arms extending from a central bulge. Our solar system is located in one of the spiral arms, about 2/3 of the way out from the center. We're in a relatively quiet region between major spiral arms, in what's sometimes called the Orion Spur. The galaxy rotates, and we rotate with it, orbiting the galactic center at about 250 kilometers per second. Even at this speed, it takes about 230 million years to complete one orbit. The last time our solar system was in this position, dinosaurs were just beginning to appear on Earth from our location in the galaxy. We can see the Milky Way as a band of light across the night sky. This band is created by the combined light of billions of stars in the galactic disk, too far and too numerous to see individually, blending together into a milky glow. Ancient cultures noticed this band and created myths to explain it. The Greeks called it Galaxias Kyklos, the Milky Circle, which is where we get the word galaxy. Many cultures saw it as a river or a path, a bridge between Earth and the heavens. Now we know it's the view from inside our own galaxy, looking toward the densest concentration of stars in the very center of the Milky Way. Hidden behind clouds of dust lies a supermassive black hole. This black hole has a mass equal to about 4 million suns, but it's packed into a region smaller than the orbit of Mercury. It doesn't actively consume much matter right now, so it's relatively quiet. But occasionally, a star or a cloud of gas strays too close, and the black hole tears it apart, consuming it in a burst of radiation. The black hole's gravity dominates the galactic center, and stars near the center orbit it at tremendous speeds, completing orbits in just a few years or decades, despite being light years away from it. Stars near the galactic center are packed much more densely than stars in our region. In some parts of the central bulge, stars are separated by distances comparable to the size of our solar system. If Earth were located there, the night sky would be spectacular, filled with bright stars, close enough that some would appear as tiny disks rather than points. There would be little darkness at night, the sky glowing with the light of thousands of nearby stars. But there would also be more danger, more radiation, more frequent close encounters between stars. Our location in a quieter region of the galaxy is probably beneficial for the development of complex life. Stars have been forming in the Milky Way for over 13 billion years, nearly the entire age of the universe. The oldest stars are called population 2 stars, and they're found mostly in the galactic halo, a roughly spherical region surrounding the galactic disk. These ancient stars are poor in heavy elements because they formed from the primordial gas that existed shortly after the Big Bang. Gas that was mostly hydrogen and helium with only trace amounts of heavier elements. Later generations of stars, called population I stars, contain more heavy elements because they formed from gas, enriched by previous generations of stars that created heavy elements and scattered them into space when they died. Our Sun is a population I star, formed from gas that had already been enriched by earlier generations. The heavy elements in our solar system, the carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these were created inside ancient stars and released into space when those stars died. We are, quite literally, made of stardust. Every atom heavier than helium in your body was forged in the core of a star that lived and died before our solar system existed. That star's death scattered those atoms into space, where they eventually became part of the cloud that formed the sun and planets, and eventually you. This process of element creation is called nucleosynthesis. It happens in the cores of stars, where temperatures and pressures are high enough to force atomic nuclei together. In main sequence, stars like our Sun, hydrogen fuses into helium. This is the simplest fusion reaction, and it releases the most energy per unit mass. 4 hydrogen nuclei combine through a series of steps to form one helium nucleus. The helium nucleus is slightly less massive than the 4 hydrogen nuclei that formed it, and that missing mass is converted to energy according to Einstein's famous equation. Energy equals mass times the speed of light squared as a star ages and uses up the hydrogen in its core. The core contracts and heats up. Eventually, it becomes hot enough to start fusing helium into carbon. This produces less energy than hydrogen fusion, but it's enough to keep the star shining. The star expands as this happens, growing larger and cooler on the surface, becoming a red giant. Our sun will do this in about 5 billion years. It will swell to perhaps 100 times its current diameter, possibly engulfing Mercury and Venus, maybe even Earth. But this transformation will take millions of years. A gradual expansion as the sun adjusts to burning helium instead of hydrogen. Red giants are beautiful in their way, enormous and luminous, glowing with a soft orange or red light. Despite their size, they're not particularly massive. They've just spread themselves out, their outer layers puffed up and diffuse. The core is small and dense, furiously burning helium. The outer layers are thin and cool, extending far into space. Some red giants pulse, expanding and contracting rhythmically as they adjust to the changing conditions in their cores. These pulsating stars vary in brightness as they pulse, growing brighter when compressed and dimmer when expanded. 4 stars more massive than the sun. The story continues beyond helium burning. When the helium is exhausted, the core contracts again and heats up further. If the star is massive enough, it can start fusing carbon into heavier elements like oxygen, neon, and magnesium. Then those elements can fuse into even heavier ones like silicon and sulfur. Each stage produces less energy than the previous one and lasts for a shorter time. Carbon burning might last for thousands of years. Silicon burning lasts only days. The star is racing toward the end of its life, trying to stave off gravitational collapse by burning whatever fuel it has left. Eventually, massive stars create iron in their cores. Iron is special because it's the most stable nucleus. Fusing iron doesn't release energy. It actually requires energy. So when a star's core turns to iron, fusion stops. There's no more fuel, no more way to resist gravity. The core collapses in a fraction of a second, falling inward at a quarter of the speed of light. This collapse is catastrophic and violent. The core becomes so dense that protons and electrons are crushed together, forming neutrons. The core becomes a neutron star, a ball of neutrons about 20 kilometers across, but containing more mass than the sun. The collapse sends a shockwave outward through the star's outer layers. This shockwave heats and compresses the material, triggering explosive fusion. Elements heavier than iron, like gold, silver, platinum, and uranium, are created in this moment. The shockwave blows the star apart in a supernova explosion, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy, releasing more energy than the sun will produce in its entire lifetime. The explosion scatters the star's material, including all the heavy elements it created, into the surrounding space. This material enriches the interstellar medium and will eventually become part of new stars and planets. Supernova explosions are both endings and beginnings. They mark the death of a massive star, but they also seed the galaxy with the elements necessary for planets and life. Without supernova, there would be no carbon, no oxygen, no iron, none of the elements that make up rocky planets and living things. Every supernova is a gift to the future, a star giving itself back to the universe, transforming into the raw material for new generations of stars and worlds. There's something poetic about that, about death leading to new life, about endings that are also beginnings. The remnants of supernova are some of the most beautiful objects in the sky. The Crab Nebula is the remnant of a supernova that exploded in the year 1054, observed and recorded by Chinese and Arab astronomers. At the center is a pulsar, a rapidly spinning neutron star that emits beams of radiation like a lighthouse. Around it is an expanding shell of gas, glowing in multiple colors from different elements, powered by energy from the pulsar. The nebula is still expanding, still growing, and it will continue to expand for thousands of years before eventually dispersing into the interstellar medium Not all massive stars end as supernova. The most massive stars, those with cores above a certain mass, collapse so completely that even neutron degeneracy pressure can't stop them. They keep collapsing, becoming black holes. The boundary where this happens is still uncertain. But probably stars with initial masses above 20 or 30 times the sun's mass will end as black holes. These stellar mass black holes are much smaller than the supermassive black holes at galactic centers. Typically, just a few to a few dozen times the sun's mass. But they're still black holes. Regions where gravity is so strong that nothing can escape. For stars like our sun, less massive stars, the ending is gentler. The sun will never become a supernova. It's not massive enough to fuse elements beyond carbon and oxygen. After it finishes burning helium in its core, the core will contract but won't get hot enough to burn carbon. The core will simply cool and solidify into a white dwarf, a ball of carbon and oxygen about the size of Earth, but containing most of the sun's mass. The outer layers of the sun will be gently expelled into space, forming a planetary nebula, a beautiful shell of glowing gas surrounding the white dwarf. Planetary nebulae have nothing to do with planets. They were named by early astronomers who thought they looked like planetary disks through small telescopes. In reality, they're the cast-off outer layers of dying stars, glowing because they're heated by the hot white dwarf at the center. These nebulae come in spectacular shapes: spheres, rings, hourglasses, butterflies. The shapes are created by complex interactions between the expanding gas, stellar winds, and sometimes companion stars. Each planetary nebula is unique, a final work of art created by a dying star. White dwarfs are the end state for most stars. They no longer undergo fusion. They're just hot, dense remnants, slowly cooling over billions of years. A white dwarf is supported not by fusion energy, but by electron degeneracy, pressure. A quantum mechanical effect that prevents electrons from being squeezed too close together. This pressure is strong enough to support the star against gravity, even though it's no longer producing energy. White dwarfs start hot, tens of thousands of degrees at the surface, but they gradually cool, fading from white to yellow to red, and eventually to black. Though this takes longer than the current age of the universe, our sun's white dwarf will be about half the sun's current mass, compressed into a sphere the size of Earth. A teaspoon of white dwarf material would weigh several tons. The atoms in a white dwarf are ionized, stripped of their electrons, and packed together as tightly as quantum mechanics allows. The electrons form a degenerate gas, moving at speeds close to the speed of light, creating the pressure that holds the star up. It's a strange state of matter, Nothing like anything we experience in daily life. But it's stable, and white dwarfs can exist in this state essentially forever. Neutron stars are even more extreme. They're what remains when a star, more massive than the Sun, collapses in a supernova, but isn't massive enough to form a black hole. A neutron star is about 20 kilometers across, but it contains between 1 and 3 times the Sun's mass. A teaspoon of neutron star material would weigh as much as a mountain. The density is so high that atoms can't exist. Protons and electrons are forced together, forming neutrons, and these neutrons are packed as tightly as the nuclei of atoms. A neutron star is essentially one giant atomic nucleus held together by gravity. The surface gravity on a neutron star is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star, you'd be flattened instantly into a layer a few atoms thick. Light has trouble escaping from a neutron star's surface because the gravity is so strong. Space and time are significantly curved around neutron stars, and all the strange predictions of general relativity become important. Neutron stars are laboratories for extreme physics, places where matter and space-time behave in ways that can't be replicated anywhere else. Many neutron stars are pulsars, spinning rapidly and emitting beams of radiation from their magnetic poles. As a neutron star rotates, the beams sweep across space like a lighthouse. If Earth happens to be in the path of one of these beams, we see a pulse of radiation each time the beam points toward us. Some pulsars spin hundreds of times per second, rotating so fast that a point on the surface is moving at a significant fraction of the speed of light. These millisecond pulsars are incredibly precise clocks, their pulses arriving with a regularity that rivals the best atomic clocks we've built. Pulsars were discovered in 1967 by Jocelyn Bell Burnell, a graduate student who noticed strange, regular pulses in radio telescope data. The pulses were so regular that they were briefly considered as possible signals from extraterrestrial civilizations, jokingly labeled LGM-1 for little green men. But further observations showed they were natural phenomena. Neutron stars spinning rapidly and emitting radiation. The discovery of pulsars confirmed the existence of neutron stars, objects that had been theoretically predicted but never observed. It was one of the great discoveries of 20th century astronomy. Some binary star systems contain a neutron star or a white dwarf paired with a normal star. If the two stars are close enough, material from the normal star can flow onto the compact companion, spiraling inward and forming an accretion disk. As this material spirals inward, it heats up due to friction and compression, eventually becoming hot enough to emit X-rays. These X-ray binaries are among the brightest X-ray sources in the sky. The accretion process is violent, with material falling toward the compact object at tremendous speeds, releasing enormous amounts of energy as it falls. In some cases, the accumulated material on the surface of a white dwarf or neutron star can ignite in a thermonuclear explosion. On a white dwarf, this creates a nova, a sudden brightening as the surface layer undergoes explosive fusion. The star might brighten by tens of thousands of times for a few days or weeks before fading back to normal. Novae can repeat if material continues to accumulate. On a neutron star, similar accumulation can lead to X-ray bursts, sudden releases of X-ray energy. These events are reminders that even dead stars, white dwarfs, and neutron stars can still be active and dynamic given the right circumstances. There's a special type of supernova called a type Ia supernova that occurs in binary systems containing a white dwarf. If the white dwarf accumulates enough mass from a companion star, it can approach the Chandrasekhar limit, about 1.4 times the Sun's mass. At this mass, electron degeneracy pressure can no longer support the white dwarf. The star collapses, and the collapse triggers explosive fusion throughout the entire star. The white dwarf is completely destroyed in a massive explosion that briefly outshines its entire host galaxy, type Ia. Supernova are remarkably consistent in their peak brightness. This makes them useful as standard candles for measuring cosmic distances. By comparing how bright a type Ia supernova appears to how bright we know it actually is, we can calculate its distance. This technique has been used to map the expansion of the universe and led to the discovery that the expansion is accelerating, driven by mysterious, dark energy. So these exploding stars, violent as they are, have taught us fundamental things about the nature and fate of the universe. Let's think about star clusters for a moment. Groups of stars that form together and remain gravitationally bound. Open clusters are loose groupings of dozens to thousands of stars, typically young, found in the galactic disk. The Pleiades, also called the Seven Sisters, is a famous open cluster visible to the naked eye. It contains about 1,000 stars formed about 100 million years ago. The brightest members are hot blue stars, young and energetic. Over time, open clusters gradually disperse as gravitational interactions with other stars and gas clouds slowly pull them apart. Globular clusters are different, much older and much more tightly packed. A typical globular cluster contains hundreds of thousands or even millions of stars, all packed into a spherical region, perhaps 100 light years across. The density of stars near the center of a globular cluster is thousands of times higher than in our neighborhood. The stars in globular clusters are ancient, often over 10 billion years old, formed in the early history of the galaxy. They orbit in the galactic halo above and below the galactic disk, following elongated orbits that take them far from the galactic center and then back again. Looking at a globular cluster is like looking at a city of stars. So many stars packed together that the cluster core appears almost as a continuous glow. Individual stars can't be distinguished in the center, only in the outer regions where the density decreases. Globular clusters are gravitationally stable. They're stars orbiting the cluster center in complex paths, held together by their mutual gravity. They've survived for billions of years and will likely survive for billions more. Ancient communities of stars drifting through the halo. The stars in a globular cluster all formed at about the same time from the same cloud of gas. So they have the same age and similar composition. But they have different masses, and mass determines a star's lifetime. The most massive stars in a cluster die first, while less massive stars live longer. By studying which stars are still present and which have already died, astronomers can estimate the age of the cluster. Globular clusters are some of the oldest objects in the galaxy, witnesses to the galaxy's early history, containing stars that have been shining since the universe was young. Variable stars are stars that change in brightness over time. Some vary because they pulsate, expanding and contracting periodically. Others vary because they're in binary systems where one star periodically eclipses the other. Some vary irregularly, flaring up unpredictably. One important class of variable stars is the Cepheid variables, named after Delta Cephei, the first star of this type to be recognized. Cepheids pulsate regularly, varying in brightness with periods ranging from a few days to a few months. The period of pulsation is related to the star's luminosity. Brighter Cepheids pulsate more slowly. This relationship between period and luminosity makes Cepheids extremely useful for measuring distances. By measuring a Cepheid's period, you can determine its true luminosity. By comparing this to how bright it appears, you can calculate its distance. Henrietta Swan Leavitt discovered this relationship in 1912 while studying Cepheids in the Magellanic Clouds, two small galaxies that orbit the Milky Way. Her discovery gave astronomers a way to measure distances across the galaxy and beyond, revolutionizing our understanding of the scale of the universe. Another type of variable star is the eclipsing binary, where two stars orbit each other in a plane aligned with our line of sight. As the stars orbit, they periodically pass in front of each other, causing regular dips in brightness. By studying these eclipses, astronomers can learn about the stars' sizes, masses, and orbits. Some eclipsing binaries have been studied in such detail that we know their properties better than we know the suns. These systems are laboratories for testing our theories of stellar structure and evolution. There are also flare stars, small red dwarfs that occasionally brighten suddenly due to magnetic activity on their surfaces. The flares are like solar flares, but proportionally much more powerful. A flare on a red dwarf can temporarily double or triple the star's brightness. These flares are caused by the star's magnetic field, which can become twisted and tangled, storing energy that's suddenly released in a burst of light and charged particles. Red dwarfs are often quite active, despite being cool and dim. Their surfaces roiling with magnetic activity. The nearest stars to our Sun are mostly red dwarfs. Proxima Centauri is a red dwarf, and it's a flare star experiencing frequent outbursts. It also has at least one planet, Proxima Centauri b, which orbits in what might be the habitable zone. But the frequent flares might make the environment harsh for life, bathing the planet in radiation. Still, the discovery of a planet around the nearest star is exciting. It suggests planets are even more common than we thought, that almost every star might have worlds orbiting it. Alpha Centauri, the star system Proxima orbits around, is actually a triple system. Alpha Centauri A and B are sun-like stars orbiting each other every 80 years. Proxima orbits this pair at a much greater distance, taking over 500,000 years to complete one orbit. From Proxima's perspective, Alpha Centauri A and B would appear as two very bright stars in the sky, far brighter than any star we see from Earth. From Alpha Centauri's perspective, our Sun would be a bright star in the constellation Cassiopeia, unremarkable except that it's there, a neighboring star among billions. Barnard Star is another nearby red dwarf, about 6 light-years away. It's notable for having the largest proper motion of any star, meaning it moves across the sky faster than any other star from our perspective. Of course, fast is relative. Barnard's star moves about 10.3 arcseconds per year, which means it would take about 180 years to move a distance equal to the moon's diameter in the sky. Still, in cosmic terms, it's racing past us. In about 10,000 years, it will be the closest star to the Sun, passing within about 3.8 light-years. Then it will continue on, and Proxima Centauri will reclaim its position as our nearest neighbor. Stars move through the galaxy, each following its own orbit around the galactic center. From our perspective, these motions make stars slowly drift relative to each other, changing the shapes of constellations over thousands of years. The Big Dipper, so familiar to us now, looked different 10,000 years ago, and will look different 10,000 years from now. The stars that form it are at different distances from us and are moving in different directions, so the pattern slowly changes. Constellations are temporary arrangements. Patterns we see from our particular vantage point at this particular time. Ancient astronomers didn't know this. They thought the stars were fixed to a celestial sphere, unchanging and eternal. The name fixed stars reflects this belief. But we know now that stars are in constant motion, orbiting the galaxy, some moving toward us, some moving away. The motion is slow from our perspective, imperceptible over a human lifetime. But over thousands or millions of years, the night sky transforms completely. The stars we see will disperse, new patterns will form. The familiar constellations will fade into history. Some stars are moving so fast that they're escaping the galaxy entirely. These are called hypervelocity stars, and they're traveling at speeds of hundreds of kilometers per second, fast enough to overcome the galaxy's gravity and fly out into intergalactic space. Most hypervelocity stars probably gain their speed through gravitational interactions with a supermassive black hole at the galactic center. A binary star system wandering too close to the black hole can be torn apart. With one star captured by the black hole and the other flung outward at tremendous speed, a gravitational slingshot effect. These ejected stars will eventually leave the Milky Way, becoming wanderers in the vast space between galaxies. The space between galaxies is truly empty, far emptier than the space between stars. Intergalactic space contains almost no matter, just a few stray atoms per cubic meter, and the distances are vast. The nearest large galaxy to the Milky Way is Andromeda, about 2.5 million light-years away. A hypervelocity star traveling at 500 kilometers per second would still take billions of years to reach Andromeda. It would be a lonely journey through darkness with no nearby stars, no planets, just the faint glow of distant galaxies in every direction. But let's return to the Milky Way, to the stars we can see and study. One of the most famous stars in the sky is Betelgeuse, the red supergiant marking Orion's shoulder. Betelgeuse is enormous, about 700 times the diameter of the Sun. If it replaced the Sun in our solar system, its surface would extend beyond the orbit of Mars. The star is also old and near the end of its life. Sometime in the next 100,000 years, possibly much sooner, Betelgeuse will explode as a supernova. When it does, it will briefly become as bright as the full moon, visible even in daylight. It will be a spectacular sight, a once-in-a-civilization event, visible to the naked eye for weeks or months. There's no danger from Betelgeuse's eventual supernova. It's over 600 light-years away, far enough that the radiation from the explosion will be harmless by the time it reaches. We'll just see a beautiful light show, a star dying dramatically in the night sky. And because the light takes 600 years to reach us, the explosion might have already happened. We won't know until the light arrives. Betelgeuse might have exploded centuries ago, and we're still seeing it as it was, waiting for the news to arrive at the speed of light. Another famous star is Sirius, the brightest star in the night sky. Sirius is actually a binary system consisting of Sirius A, a main sequence star about twice the Sun's mass, and Sirius B, a white dwarf. Sirius B is one of the first white dwarfs detected in 1862. Because of its gravitational effect on Sirius A, the two stars orbit their common center of mass every 50 years. Sirius B is much dimmer than Sirius A, but very dense, containing about the Sun's mass in a sphere roughly the size of Earth. Sirius is only 8.6 light-years away, quite close in cosmic terms, which is why it appears so bright. Its name comes from the ancient Greek word Sirios, meaning glowing or scorching. Ancient cultures around the world noticed and named Sirius. The Egyptians based their calendar on the heliacal rising of Sirius, the first day each year when the star became visible in the dawn sky before sunrise. This event occurred around the time of the Nile's annual flooding, an important event for Egyptian agriculture. The star was associated with the goddess Isis and played an important role in Egyptian religion and culture. Polaris. The North Star is another famous star, important for navigation because it's located almost directly above Earth's North Pole. As Earth rotates, Polaris appears to stay in the same place while other stars circle around it. Sailors have used Polaris for centuries to find their direction and latitude. The star's height above the horizon corresponds to your latitude. At the equator, Polaris is on the horizon. At the North Pole, it's directly overhead. This simple relationship made celestial navigation possible long before GPS and modern technology. Polaris is actually a multiple star system. The main star, Polaris A, is a supergiant about 430 light-years away. It's also a Cephid variable, though its pulsations are small and slow. Polaris has two smaller companion stars orbiting it. The system is complex and still being studied. But for navigation purposes, Polaris appears as a single point of light, conveniently located near the celestial pole. A gift of chance geometry that has guided travelers for millennia. The position of the celestial pole isn't fixed forever. Earth's axis wobbles slowly in a motion called precession, taking about 26,000 years to complete one cycle. As a result, the celestial pole traces a circle in the sky over this period, and different stars take turns being the pole star. 5,000 years ago, During the time of the ancient Egyptians, the pole star was Thuban in the constellation Draco. In about 12,000 years, Vega will be the pole star. Then the pole will drift to other stars before eventually returning to near Polaris. It's another reminder that even the apparently fixed features of the sky change. Given enough time, Vega is a beautiful blue-white star, one of the brightest in the summer sky for Northern Hemisphere observers. It's about 25 light-years away and about twice the Sun's mass. Vega rotates rapidly, completing one rotation every 12.5 hours compared to the Sun's 25 days. This rapid rotation flattens the star, making it wider at the equator than at the poles. Vega is surrounded by a disk of dust, debris left over from its formation, and possibly from collisions between asteroids and comets in a planetary system. We haven't detected planets around Vega yet, but the dust disk suggests they might be there. Asterisk, Arcturus is a red giant, one of the brightest stars in the sky, visible as a warm orange point of light. It's about 37 light-years away and about 25 times the Sun's diameter. Arcturus is old, probably about 7 billion years, and has already exhausted the hydrogen in its core. It's now burning helium in the red giant phase that the Sun will enter in about 5 billion years. Eventually, Arcturus will shed its outer layers and become a white dwarf. But for now, it shines brightly, a preview of our Sun's future. Rigel, another star in Orion, is a blue supergiant, one of the most luminous stars visible to the naked eye. It's about 800 light-years away and shines with a light of about 120,000 suns. If Rigel were at the same distance as Sirius, it would cast shadows at night and be visible during the day. But it's far away, so it appears as just one of many bright stars, distinguished mainly by its blue color. Rigel is massive, about 20 times the Sun's mass, and will end its life in a supernova explosion. Though that's probably millions of years away. Antares is a red supergiant in the constellation Scorpius. Its name means rival of Mars because it shines with a similar red color and can be confused with a planet. Mars, when they're near each other in the sky. Antares is huge, about 700 times the Sun's diameter. Large enough that if it replaced the Sun, its surface would extend beyond the orbit of Mars. The star is relatively close, only about 550 light-years away, and will eventually explode as a supernova. Like Betelgeuse, it's near the end of its life. Though near in astronomical terms still means potentially thousands or tens of thousands of years. Deneb is one of the most distant stars visible to the naked eye. Roughly 2,600 light-years away. It's a blue-white supergiant, incredibly luminous, shining with the light of about 200,000 suns. This enormous luminosity is why we can see Deneb, despite its great distance. Most stars at that distance are too faint to see without a telescope, but Deneb is so bright that it's easily visible. One of the brightest stars in the summer sky for Northern Hemisphere observers. It marks the tail of Cygnus, the swan, and is part of the summer triangle. Asterism, along with Vega and Altair. The variety of stars is wonderful. Each one is unique, with its own mass, temperature, age, composition, and evolutionary stage. Some are newborns, just beginning to shine. Some are middle-aged, steadily burning hydrogen, like our sun. Some are elderly, swollen into giants, or collapsing into white dwarfs. Some are violent, exploding, or consuming companions. Some are quiet, just existing, converting mass to energy, shining steadily for billions of years. And all of them are following the same physical laws. Their lives determined by their mass and composition. Their fates written in the equations of nuclear physics and gravity. There's something peaceful about understanding that stars follow predictable patterns. We can calculate how long a star will live based on its mass. We can predict when it will leave the main sequence, how large it will become as a giant, whether it will end as a white dwarf or a neutron star or a black hole. The universe is knowable. The processes that govern stars are comprehensible. We've figured out how stars work, not through magic or mythology, but through careful observation and logical reasoning, through physics and mathematics. The universe makes sense, and that's deeply comforting. Star formation is still happening today throughout the galaxy. The Orion Nebula is one of the closest star-forming regions, about 1,300 light-years away. It's visible to the naked eye as a fuzzy patch in Orion's sword. But through a telescope, it reveals intricate structure, glowing gas in shades of red and green, dark dust lanes, and newly formed stars scattered throughout. The nebula is a stellar nursery, a place where stars are being born right now, where the slow process of gravitational collapse and heating is transforming clouds of gas into new suns. Some of the stars in the Orion Nebula are very young, less than 1 million years old. They're still surrounded by the disks of gas and dust from which they formed. These protoplanetary disks are where planets are forming, the same process that created our solar system 4.5 billion years ago. We can see this process happening in real time, observing disks around young stars, watching as planets coalesced from the dust. It's like watching the birth of new worlds, new solar systems coming into existence. In a few million years, those disks will be gone. cleared away by the young star's radiation and wind. And in their place will be solar systems with planets, asteroids, and comets. The youngest stars are often hidden inside their natal clouds, still embedded in the gas and dust from which they formed. These protostars are invisible in optical light because the surrounding dust blocks visible light, but they glow brightly in infrared, and infrared telescopes can peer through the dust to see the forming stars inside. Infrared astronomy has revealed countless protostars, showing us that star formation is an ongoing process, that the galaxy is constantly creating new stars to replace the ones that die. Some star-forming regions are more active than others. The Tarantula Nebula in the Large Magellanic Cloud is one of the most active, forming stars at a rate far higher than anywhere in the Milky Way. The nebula is so bright that if it were at the same distance as the Orion Nebula, it would cast shadows on Earth at night. It's a massive star factory, creating hundreds or thousands of stars, including some of the most massive stars known. These massive stars have short lives and will soon explode as supernova, enriching the nebula with heavy elements and possibly triggering new waves of star formation with their shock waves. Star formation can be triggered by various mechanisms. Sometimes a cloud just becomes dense enough to start collapsing on its own. Sometimes a shock wave from a nearby supernova compresses a cloud, triggering collapse. Sometimes galaxies collide, and the collision compresses gas clouds, sparking intense bursts of star formation. The mechanisms vary, but the result is the same. Gas collapses, heats up, and eventually ignites as a new star. It's a process that's been happening since the early universe, that's still happening today. That will continue for trillions of years until the gas runs out. The interstellar medium, the gas and dust between stars, is the raw material for star formation. It's thin, averaging about 1 atom per cubic centimeter, but spread across the vast space between stars, it adds up to a significant amount of matter. The gas is mostly hydrogen and helium, the primordial elements from the Big Bang, mixed with heavier elements created and dispersed by earlier generations of stars. The dust consists of tiny grains of carbon, silicates, and ice, each grain smaller than the particles in smoke, but collectively forming clouds that block light and provide surfaces where molecules can form. These dust grains are crucial for planet formation. When a protoplanetary disk forms around a young star, the dust grains stick together when they collide. Over time, they build up into larger and larger objects: pebbles, rocks, boulders, asteroids, and eventually, planets. The process is similar to how snowflakes stick together to form a snowball. The dust grains are the building blocks of worlds. And those grains were themselves created in the atmospheres of dying stars and in supernova explosions. So planets are made from the remains of dead stars. Another way in which stellar death leads to new creation. Molecules can form on the surfaces of dust grains where atoms meet and bond together. The interstellar medium contains surprisingly complex molecules, including water, ammonia, methanol, and even amino acids, the building blocks of proteins. These molecules are created in space, in the cold, thin clouds between stars. Through processes we're still working to understand. Some of these molecules are delivered to planets by comets and asteroids, possibly playing a role in the origin of life. The chemistry of space is rich and complex, and it connects stellar processes to planetary processes to the possibility of life. Asterisk stars are connected to everything. They create the elements that make up planets and life. They heat and illuminate planetary systems, providing energy for life to use. Their gravity holds solar systems together. Their radiation drives the chemistry of planetary atmospheres. When stars die, they enrich the interstellar medium with heavy elements, making possible the next generation of stars and planets. The cycle continues, stars forming and dying, matter cycling through different forms, the galaxy slowly enriching itself with heavier elements over billions of years. Our sun is part of this cycle. It formed from a cloud enriched by previous generations of stars. When it dies, it will return its material to space, enriching the interstellar medium with carbon and oxygen from its core. That material might eventually become part of new stars, new planets, maybe even new life. The atoms in your body have been through this cycle many times already. They've been part of other stars, other planets, other organisms. You're not just made of stardust. You're made of recycled stardust. Atoms that have been through the cosmic furnace multiple times, transformed and retransformed. Temporary patterns in an ongoing dance of matter and energy. Every star you see is part of this story. Some are young, just beginning their journey. Some are old, nearing the end. Each one is at a different stage in the stellar life cycle. From protostar to main sequence, to giant, to white dwarf, or neutron star, or black hole. The variety is immense, but the underlying pattern is universal. Mass determines fate. The laws of physics are the same everywhere. Stars are comprehensible, predictable, part of a cosmic order that's both beautiful and comforting in its regularity. As we enter the final part of our journey through the stars, let's think about what it means to look up at the night sky and see those distant points of light. Each star is a sun, potentially with its own family of planets. Each represents a place, a location in space where matter and energy are organized in a particular way, where fusion is happening, where light is being created. The stars are real, physical objects, not just decorations on a celestial dome, but actual spheres of hot plasma floating in the void, separated by distances so vast we measure them in years of light travel. When ancient peoples looked at the stars, they saw patterns and created stories. The constellations were heroes and animals, tools and monuments, stories written across the sky. These stories helped people remember the patterns, helped them navigate, helped them mark the seasons. The rising and setting of certain stars indicated when to plant crops, when to expect rain, when winter was coming. The stars were a calendar, a clock, a map, all combined into one. We still use those ancient constellation names, even though we know the stars aren't actually connected, that they're at vastly different distances, that the patterns are accidents of perspective. Orion the hunter isn't a real giant in the sky. The stars that form his figure are hundreds of light years apart, scattered through a large volume of space. From another angle, from another star system, those stars wouldn't form any recognizable pattern at all. The constellations are meaningful to us because of where we are, because of the stories we've told. But they're not intrinsic to the stars themselves. Yet there's something beautiful about that. The constellations exist at the intersection of nature and culture, of physical reality and human imagination. The stars are real, their positions are real, but the patterns we see are our creation. We've imposed meaning on the random scatter of stars, found order in chaos, created navigation, aids, and storytelling devices from the raw material of distant suns. It's a very human thing to do, finding patterns, creating meaning, connecting disparate objects into coherent wholes. Modern astronomy has revealed so much more than ancient astronomers could have imagined. We know what stars are made of by studying their light. When light passes through a prism or a diffraction grating, it spreads into a spectrum, a rainbow of colors. But the spectrum isn't continuous. There are dark lines where specific colors are missing, absorbed by atoms in the star's atmosphere. Each element produces a unique pattern of lines, a fingerprint that identifies it. By studying stellar spectra, we can determine what elements a star contains and in what quantities. This technique, called spectroscopy, revolutionized astronomy in the 19th and 20th centuries. It revealed that stars are made of the same elements found on Earth, that the universe is fundamentally unified in its composition. The same hydrogen and helium that make up stars also exist here. the same carbon and oxygen, the same iron and silicon. The universe isn't divided into separate realms with different substances and different laws. It's all one system operating according to the same principles everywhere. Spectroscopy also reveals motion. When a star moves toward us, the light waves are compressed, shifted toward shorter wavelengths, toward the blue end of the spectrum. When a star moves away, the light waves are stretched, shifted toward longer wavelengths, toward the red end. This Doppler shift is how we measure the velocities of stars, how we know some are approaching and others receding, how we map the rotation of the galaxy. It's also how we detect planets around other stars. As a planet orbits a star, the star wobbles slightly, pulled by the planet's gravity. This wobble causes tiny Doppler shifts in the star's light, rhythmic changes that reveal the presence of an orbiting planet. Thousands of exoplanets have been discovered this way, and through other methods like watching for the dimming when a planet passes in front of its star. The discoveries have been remarkable. Planets come in incredible variety, configurations we never imagined before we started looking. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Super Earths with masses several times Earth's. Planets orbiting binary stars, seeing to sunrises each day. Planets in extreme orbits, highly elliptical or tilted at odd angles. Planets around pulsars, somehow surviving the supernova that created the pulsar. The diversity suggests that planet formation is robust, able to produce worlds in almost any imaginable circumstance. Some exoplanets orbit in their star's habitable zone, the region where temperatures could allow liquid water. These are the worlds that most capture our imagination. The possibility that somewhere on those distant planets, life might exist. We don't know yet. We can't yet analyze the atmospheres of small rocky planets in detail, though that capability is coming. The James Webb Space Telescope and future missions will be able to study the atmospheres of Earth-sized planets, looking for gases like oxygen and methane that might indicate life. We're on the verge of being able to answer one of humanity's oldest questions: are we alone? Even if most planets don't have life, the fact that they exist, that nearly every star has planets, is profound. The galaxy contains hundreds of billions of stars, which means hundreds of billions of planetary systems, trillions of individual worlds. Each world is unique, with its own geology, its own weather, its own story. Rocky worlds baked by their stars, ice worlds in the outer reaches of their systems, gas giants with storms larger than Earth, moons orbiting those giants, some perhaps with subsurface oceans. The variety is staggering, and we've only just begun to explore it. within our own solar system. We've sent probes to every planet and many moons. We've landed on Mars, Venus, Titan. We've flown past Pluto and beyond. We've learned that many moons are geologically active, that Europa and Enceladus likely have liquid oceans beneath their icy crusts, that Titan has lakes and rivers of liquid methane. Our solar system is far more dynamic and interesting than we thought. And if our system is this complex, imagine the diversity across billions of other systems, each with its own configuration of planets and moons, each with its own unique features and phenomena. Stars enable all of this. Without stars, there would be no planets, or at least no warm planets where liquid water could exist. Stars provide the energy that drives planetary atmospheres and climates. Stars create the heavy elements that make up rocky planets. Stars illuminate worlds, allowing photosynthesis, warming surfaces, creating temperature gradients that drive weather. Stars are the anchors of solar systems, the gravitational centers that hold families of worlds together. Life as we know it requires a star, requires that steady supply of energy, requires a stable environment that only a long-lived star can provide. Our sun has been stable for billions of years and will remain stable for billions more. This stability has allowed life on Earth to evolve, to develop complexity, to fill every available niche. If the sun varied significantly in output, if it dimmed or brightened by even a few percent, Earth's climate would change dramatically, potentially making life difficult or impossible. But the sun doesn't vary much. It shines steadily, reliably, providing a consistent environment. This is true of most stars. Once they settle onto the main sequence, they're stable, burning hydrogen at a steady rate for millions, billions, or trillions of years, depending on their mass. Asterisk, there's deep comfort in that stability. The sun will rise tomorrow and the next day, and every day for the rest of your life, and for billions of years beyond. The stars will continue shining, continuing their patient work of converting hydrogen to helium, releasing light and heat, maintaining the cosmic order. The processes are automatic, reliable, requiring no maintenance or intervention. Stars just do what stars do, following the laws of physics, being exactly what they are, perfectly, completely, without effort or struggle. As you rest here, thinking about stars, consider your connection to them. The light you see from stars left those stars years or centuries or millennia ago. You're seeing them as they were in the past. But in a sense, the connection is more immediate than that. The light is here now, arriving at your eye now. Photons that have traveled across space to reach you specifically. Those photons were created in the star's core, perhaps thousands of years ago, worked their way to the surface, were released into space, traveled across light years, and arrived here at this moment to be absorbed by your retina. There's something almost magical about that, about the directness of the connection between you and a distant star. And the connection is even deeper than light. You're made of material created in stars. The calcium in your bones was forged in the core of a massive star billions of years ago, then scattered into space when that star exploded. The iron in your blood was created the same way in a supernova explosion. The carbon that forms the backbone of every molecule in your body came from a dying red giant that puffed its outer layers into space. These atoms drifted through the galaxy, eventually becoming part of the cloud that formed our solar system. They were incorporated into Earth, cycled through air and water and rock, and eventually became part of you. You're not just observing the universe from outside. You're part of it, made of it. A temporary arrangement of atoms that have existed since shortly after the Big Bang. Those atoms have been through countless transformations, have been part of countless other structures, and will continue existing long after you're gone. You're a momentary pattern in an ongoing flow of matter and energy, a brief expression of complexity in the universe's long history. And that's not diminishing. It's elevating. You're part of the story, part of the cosmic narrative that connects the Big Bang to the formation of galaxies, birth and death of stars to the emergence of planets and life. The stars have been guides and inspirations for all of human history. They've helped sailors navigate oceans. They've helped farmers know when to plant. They've inspired religions and philosophies. They've been the subject of countless poems and songs and paintings. People have always looked up and wondered, felt small beneath the vast sky, felt connected to something larger than themselves. That connection is real. We are connected to the stars, not metaphorically, but literally, through the atoms we're made of, through the light that reaches us, through the processes that created both us and them. In the future, humanity might travel to the stars. We've already sent probes beyond the solar system. Voyager 1 and 2, Pioneer 10 and 11, New Horizons, all are headed into interstellar space, though they'll take tens of thousands of years to reach even the nearest stars. Faster missions might be possible with new technology. Some scientists propose using light sails, spacecraft pushed by powerful lasers, that could reach a significant fraction of light speed and arrive at Proxima Centauri in just a few decades. Such missions are beyond our current capability, but not beyond imagination or physics. They're possible in principle, waiting only for the technology and the will to make them happen. Even if we never travel to the stars physically, we can still explore them. Telescopes keep getting better, revealing more detail, seeing farther, detecting fainter objects. We're in a golden age of astronomy, discovering new things constantly, rewriting our understanding of the universe regularly. Each generation of telescopes reveals phenomena the previous generation couldn't see. Radio astronomy revealed pulsars and cosmic background radiation. X-ray astronomy revealed binary systems with black holes and neutron stars. Infrared astronomy revealed protostars hidden in dust clouds. Gravitational wave astronomy, only just beginning, is revealing colliding black holes and neutron stars, opening an entirely new way of observing the universe. Future telescopes will be even more powerful. Projects are planned for telescopes with mirrors tens of meters across, able to image the surfaces of nearby stars, to study the atmospheres of Earth-like exoplanets in detail, to see the first stars that formed after the Big Bang. Space-based interferometers might be able to directly image planets around nearby stars, to see their countenance and oceans if they have them, to search for signs of life or civilization. The possibilities are extraordinary, limited only by technology and funding, not by physics. We can imagine knowing within the next century or two whether life exists on planets around other stars. We might know whether we're alone or part of a larger community of living worlds. But even if we never find life elsewhere, even if Earth turns out to be unique, the stars will still be beautiful and meaningful. They're still the factories that create elements, still the anchors of planetary systems, still the light sources that illuminate the galaxy. They're still part of the great cycle of matter and energy that makes the universe dynamic and interesting. And they're still symbols of a vast scale and age of the cosmos, reminders that we're part of something much larger than ourselves, something that existed long before us and will continue long after we're gone. As you drift toward sleep, let yourself relax into this perspective. You're resting on a planet orbiting a star, one of hundreds of billions in the galaxy. Above you, separated by vast distances, countless other stars shine, each one a nuclear furnace, each one steadily converting mass to energy, lighting up the darkness. Some of those stars have planets. Some of those planets might have life. Most are probably barren, but all are interesting. All are worlds with their own features and stories. The universe is full, not empty. Everywhere you look, there's something, some structure, some object, some process unfolding, and it's all happening according to understandable laws. Gravity pulls matter together. Fusion releases energy. Light travels at a constant speed. Atoms have specific properties. These rules are consistent everywhere, at all times. The universe is knowable, comprehensible, governed by patterns we can discover and understand. There's order beneath the apparent chaos, structure underlying the complexity, and that order is beautiful, elegant, simple in its fundamentals, even when complex in its manifestations. You don't need to understand all the details to appreciate the beauty of a starry night. You don't need to know about nuclear fusion to feel wonder when you look at a Milky Way. The emotional and aesthetic experience of the stars is available to everyone, requiring only a dark sky and a sense of wonder. But understanding does add something, a deeper appreciation, a sense of connection, a recognition that the light you're seeing carries information about distant objects, that you're part of the same system as those distant stars, made of the same substance, governed by the same laws. So rest now, knowing that above you, whether you can see them or not, the stars continue their patient work. Fusion reactions happen in their cores, converting hydrogen to helium, releasing energy that slowly works its way to the surface and then streams out into space. Some of that light will travel for years or centuries and eventually be seen by someone else. Somewhere else, connecting beings across time and space through the simple act of observation. The stars are bridges, connecting past to future, connecting different parts of the galaxy, connecting the physical to the philosophical, the scientific to the spiritual. Let your breathing slow and deepen. Feel the weight of your body resting on this planet, this rocky world circling a yellow star on the outskirts of a spiral galaxy. Feel the stability, the solid ground beneath you, the atmosphere above you, the protective magnetic field surrounding you. You're safe here, in this small bubble of habitability in the vast cosmos. The universe is mostly empty and cold, but here, on Earth, conditions are just right for life, for consciousness, for the universe to become aware of itself. And that awareness, that ability to look up and understand what you're seeing, is one of the universe's great achievements. Matter and energy, organized in just the right way, can think, can wonder, can create models and theories, can predict the future and reconstruct the past. Stars created the elements that make up your brain. The same processes that power stars, the same quantum mechanics and thermodynamics, also govern the neurons in your brain, the thoughts you're thinking. You're not separate from the physical universe. You're an expression of it, a way the universe has of experiencing itself. Asterisk. The stars will shine tonight and tomorrow night and for billions of years to come. Some will die, exploding or fading away. New stars will be born, igniting in nebulae, beginning their long lives. The cycle continues, has always continued, will always continue as long as there's gas to form stars. And even when the gas runs out, even when the last star dies, even when the universe is dark and cold, it will still exist. Will still be following the laws of physics, will still be the arena in which matter and energy play out their eternal patterns. For now, for this brief moment, you have the privilege of being here, of being conscious, of being able to appreciate the stars. You can look up and see light from distant suns. You can understand, at least in broad strokes, what those lights are, where they came from, where they're going. You can feel wonder at the scale and beauty of it all. This capacity for wonder, for appreciation, for understanding is precious. It's what makes us human. It's what connects us to the cosmos. It's what makes this moment, this brief flicker of consciousness in the vast dark, meaningful. Close your eyes now, if you haven't already. Let the image of stars fade from your mind, but keep the feeling, that sense of connection, that peace that comes from understanding your place in the universe. You're small, but not insignificant. You're brief, but not meaningless. You're a part of an ongoing story that stretches from the Big Bang to the end of time. A story written in atoms, in energy, in gravity, and light. In the patient processes that build up stars and planets, and eventually life and consciousness. Rest in that knowledge. Let it soothe you. The stars are there, always there, whether you can see them or not. The sun will rise tomorrow, as it has every day for 4.5 billion years. The galaxy turns, the universe expands, and all of it follows patterns, operates according to laws, makes sense in a deep and beautiful way. You don't need to control any of it. You don't need to worry about it. It's all working perfectly, has been working for billions of years. Will continue working long after you're gone. Sleep now, secure in your place in the cosmos. You're safe on this world, protected and nurtured by a stable star, surrounded by the patient light of countless other stars. Part of a universe that's vast and ancient and beautiful beyond measure. The stars shine for no one and everyone, their light traveling through space, carrying energy and information, connecting everything to everything else, and a web of light and gravity and time. And you're part of that web, connected to it all. A conscious node in the universe's great network, awake for a brief time to witness and wonder before returning to the elements, completing your part of the eternal cycle. The stars are singing, have always been singing, their voices carried on light waves across the void. It's a slow song, measured in billions of years, but it's there. The harmony of fusion and gravity, the rhythm of birth and death, the melody of matter and energy dancing through space and time. You've heard that song tonight, felt its peace, understood its meaning. Now, let it lull you to sleep. Let it carry you into dreams. Let it remind you that you're part of something vast and beautiful and good. The stars are shining now and always, patient and eternal. The universe's way of lighting the darkness, of creating warmth in the cold, of making something from nothing. Endlessly, beautifully, perfectly. Good night.